Welcome to this new video. In this video, we're going to address the testing hypothesis for a new setup this time. It's going to be about testing hypothesis for paired samples or paired group. I'm going to start with an example and see if I can take this example step by step to explain how this is done. So the example we have is coming from a very famous book about biostatistics. It's called Introduction to Biostatistics by Daniels, and it's one of your reference book if you want to look it up. Part of chapter 7, there's a list of exercises, and I have made copies of these exercises, and actually they are available for you if you want to go and check them out. Example 7.4.1 is the example I want to address today. So it reads, a journal article by Kashima et al. Described research with parents of mentally retarded children in which a media-based program presented, primarily through videotapes and instructional manual, information. So this program presented information on self-help skills teaching. As part of the study, 17 families participated in a training program but led by experienced staff member of a parent training project. So basically they had 17 families and they gave them some sort of a training, and then what they were interested in is looking at the before and after. So before and after the training program, the behavior vignette test was administered to the primary parent in each family. The test assesses knowledge of behavior modification principles. A higher score, right there, sorry. So a higher score indicates a greater knowledge. And the following are the pre and post-training scores made by the primary parent on the test. So basically what you are provided with is a pre-test and post-test for a certain type of score. And I guess the question is, may we conclude on the basis of these data that the training program increased knowledge of behavior modification principle? We're going to ignore the alpha that they're suggesting of 0.01 for now. We're going to more focus on what we have as an example. So basically what do you have? We have 17 families. They were trained on a certain topic. And before the training and after the training, the primary parent was tested for their knowledge. So you have the pre-score and you have post-score, and they want to know how much there was a change in that. Okay, so the first family, the value pre was 7 and it increased to 11, so you can see that there was an increase. The second family, it was 6 and it increased to 14. The third family, it was 10 and it increased to 16, and so on and so forth for the 17 families. So how do we analyze this data? How do we interpret, how do we work with this data? So first of all, I want to show you what I did on Excel. See if I can do that. Okay, so here you have the exact same values of the 17 families. So I call them family of child 1, child 2, all the way to child 17. And I just copied the pre-value of these 17 families, and I copied the post value of these 17 families. Now notice what is important, or what is interesting here, is that for every family, for every member, you have a pre and a post. Therefore, you can actually calculate the difference, or you want to call it difference, you want to call it change, you want to call it increase, you call it whatever you want to call it. So I can calculate how much the knowledge increased, for example, for family 1, family of child 1. So it used to be 7 and it went up to 11. I can write a formula where I say, okay, let's see the difference. How much did it increase? It increased mean 11, mean 7 all the way to 11. So actually the difference is 4. So family 1 increased the score by 4 units. what happened to family 2? I'm just going to copy the formula, and like that, now I have copied the formula for these 17 families. So now family 1 has an increase of 4 units, family 2 8 units, family 3 6 units, family 4 1, family 5 1, etc. Okay, if you if you notice, what happened really is that we started up with 2 measurements for every family, for every unit, and because these 2 measurements belong to the same person, we were able to calculate a difference, and hence we now have only one set of values representing the 17 families. So really, we moved from a situation where we had 2 measurements back to a setup where we only had 1 measurement. Hopefully, you've seen how we turn this into the one sample test or scenario that we have introduced previously. And now what I need to do is I need to see what is the average. So let me calculate the average. Actually, I'm going to calculate the average per, so average or mean, right? You know that. I can call it mean. So I'm going to calculate the average for every group, and I'm also going to calculate the standard deviation S for every group. And there is a formula that you can look it up. It's very easy. You just type average, and by just picking the values that you want to calculate the average for, there we go. So the average pre-training was 10.76. The average after training went up to 14.11, which brings the differences average to 3.35. And if you're someone who likes to do the calculation, you can notice that 14.11765 minus 10.76 is actually 3.35. What about the standard deviation? Again, there's a formula. You just type in standard and pick the standard deviation with an S. It's for the sample, not a population. And again, we're going to pick the 17 values. So the standard deviation was 3.65 before to 3.22 after, and for the differences, it's 2.26. Of note, the standard deviation, you cannot take the difference of the standard deviation to get to the standard deviation of the differences. For the average, you can, okay? So again, what does that mean? It means that I used to have 2 observations per member, and now I turned it into only 1 observation per member. So in fact, I can hide these 2 columns, and I can just focus on this column, which takes me back to the scenario of having only 1 sample. And here I can actually do my regular steps. I can start asking the research question, is there evidence that these differences come from a population where the mu difference is equal to 0? And I can do my 7 steps. So let's see how this actually works. So what have we done? Well, we said that we had previously, if you remember when we were doing the testing hypothesis, the hypothesis we tested previously was for mu equal a certain value, right? So it used to be a certain value determined by the research question, or we were testing proportion equal a certain value also determined by the research question. And here we had 2 scenarios. Either we were going to use the Z or we were using the T, whereas down here we always use the Z because there's no T that covers this scenario, okay? All right, so what happened in the example we talked about? Well, in the example we talked about, we started with having 2 samples of data, But because they were paired, because you had the same people here and here every time, you were able to calculate the difference. So take that value minus that value, and we were able to get a new set of data that we call the difference. And now we were back to only having one sample, and we're going to deal only with one sample. How do we deal with that sample? Well, exactly how we used to do it before. The first step is you define your null hypothesis. Your null hypothesis is going to be that mu is equal to something. But notice that here the mu is a mu of differences, okay? Because now I'm only interested in differences. And according to the null hypothesis, remember the null hypothesis state that there's nothing going on, there's no change, no difference. Things are at their natural state. In other words, the null hypothesis says that there's no change. Okay, so that turns into the null hypothesis that the mu of differences is equal to 0. The alternative hypothesis is going to be that the mu of differences is not equal to 0. Okay, another way to state the same hypothesis is to say that the mu before equal mu after. Okay, mu before equal mu after is exactly as saying that the mu differences is equal to 0. So this is step number 1. Step number 2 is still the same thing. You're going to assume that the null is true, okay, and you're going to set alpha. So alpha, if nothing else is stated, we set it at 0.05, okay. Step number 3, you're going to calculate the test. Now, which test are we going to calculate? Well, here's the thing. In that scenario, now we only have differences, okay? Now, remember that the t-test that we used to work with used to be x bar minus mu over standard deviation in the sample divided by square root of n. Okay, so we're going to actually use the same t-test, but we're going to call things differently just so that we remember that we're dealing with differences. So instead of saying x bar, I'm going to see d bar. So it's the average of the differences, okay? And minus mu, well, this mu is the mu of differences. And since I'm assuming the null to be true, and since the null is saying that mu of differences is equal to 0, then this becomes 0 and I can drop it. So the formula becomes d bar divided by the standard deviation. Well, standard deviation of what? The before, the after, or the differences? Well, remember, we're only working with the differences. So it's actually the standard deviation of the differences, and you're going to divide it by the square root of n. And n here stands for the sample size that is inside before, inside after, meaning that the number of pairs. So if you had 17 measurement before and 17 measurement after, that is going to lead you to have 17 measurement of differences, and that is going to be your n. And remember, in n, a t has always a degrees of freedom so far that is equal to n minus 1. So if we want to apply what we did on our example, let's go back and check what were these values. What was the value of the d bar? What was s? Well, I remember that the square root of n was 17, so I'm just going to write here 17. What was d bar? Let's see. D bar was 3.35 and S of differences was 2.26. So 3.35 and 2.26. If I'm not mistaken, that should give me, all right, exactly, okay? Type. What is that value equal to? Let me do a quick calculation. First, I'm going to calculate the standard error, which is the standard deviation divided by the square root of 17. Okay, then I'm going to calculate the t, which is the average divided by the standard error. 6.11 is the value of the t. So I go back here. This actually was equal to 6.11. For degrees of freedom, 16. Okay? All right. So I'm just going to clean up a little bit so that we can continue. All right. So we finished step number 1, step number 2, step number 3. We calculated the test. So now that we know that the t came out to be equal to 6.11, step number 4 is to get the p-value. And the p-value is the probability that t, degrees of freedom 16, is as extreme as or more extreme than 6.11. Okay? Now, if you remember, the t has a normal distribution like that. It's centered at 0. The t that we calculated is 6 point something right here. Okay? So the as extreme as is going to be that area here, but it's also going to be the mirror image of that area. So it's going to be right here. So you calculate one of the two and you multiply by 2. I can actually write the p-value. I can write it as the probability of t greater than 6.11 and multiply that by 2. Okay, for degrees of freedom 16. Now, let's see if I can find that value. Okay, okay. So everything I learned before about the t applies. I need to go to degrees of freedom 16 right here, and I'm looking for the value 6. Now notice you go all the way till the end and still you haven't found 16. So the greatest value is 4.015, which is for an area of 0.9995. So how do I interpret this? Okay, so that means that if I was looking up the t, my t stops at 4 point something, and it has an area below that is 0.9995. Okay, meaning that the area above 4 point something is 0.0005. Okay, and yet my actual probability is still yet smaller than this. Okay, so but remember, I need to multiply by 2 to get to the p-value. So that probability right here, before I multiplied by 2, is actually, the probability is somewhere between two values. It's definitely smaller than 0.0005, but it's definitely greater than 0.0000, meaning 0. Okay, now to turn this into a p-value, I need to multiply by 2. So now I can write that the p-value is definitely smaller than 0.001 and definitely greater than 0. That is my p-value, step number 4. Now, step number 5, you need to do what? Well, you need to compare this to alpha. Remember what was alpha? We set our alpha to be at 5%, 0.05. This p-value is definitely less than this alpha. When the p-value is less than alpha, what is our statistical conclusion? Our statistical conclusion is that we actually reject the null hypothesis. So we got to a place where the p-value was less than alpha, so we're going to reject the null hypothesis. The null hypothesis used to say what? Well, the null hypothesis used to say that the mu of differences is equal to 0, or in other words, that the mu of the before is equal to the mu of after, meaning that there was no change in knowledge. Well, based on what we just said, we're rejecting that mu, and therefore we conclude that we have evidence, not proof. We have evidence to suggest that actually the differences is different than 0. There is a change in knowledge. Now, how do you know if that change is increasing or decreasing? Let's go back to our data, okay, and let me unhide the results. Okay, see what happened? The pre-test was 10 point something, the post-test was 14. So now I can talk about evidence that the training increased the knowledge of the main parent by, on average, 3 values. And that is what is called the paired t-test. Okay? This is called the paired t-test because you have pairs of data for the same individual or same unit of analysis, before, after, or condition 1, condition 2, and you're able to calculate per unit of analysis a difference between the two, and then you're back to your one sample test. And notice here we always use the t-test, we do not use the z-test, because we do not claim that we have sigma of differences. We're just going to stick with the standard deviation of differences provided to us from the sample. Let me do a very quick another example. Here's another example. We're going to do it quickly. The purpose of an investigation by Alahuta et al. Was to evaluate the influence of extradural block for elective caesarean section simultaneously on several maternal or fetal hemodynamic variables and to determine if the block modified fetal myocardial function. The study subject were 8 healthy parturients in gestational weeks 38 to 42. So I have 8 subjects with uncomplicated singleton pregnancies undergoing elective caesarean section under extradural anesthesia. Among the measurement taken were maternal diastolic arterial pressure. So this is my outcome, the diastolic blood pressure during 2 stages of the study. The following are the lowest value of the variables in the 2 stages. So you have stage 1 and you have stage 2. And if you count how many values you have, well, 1, 2, 3, 4, 5, 6, 7, 8, because we have 8 women and every woman is providing 2 values. Let's read the question. Do these data provide sufficient evidence at a 0.05 level, yani alpha of 0.05, to indicate that in general, under similar condition, mean maternal diastolic arterial pressure is different at the 2 stages? Okay. So how do I set it up? Okay, let's go back here, clean up. Okay, so now let's write the 7 steps. Step number 1, I need to write my null hypothesis. Now remember, the null hypothesis state that there's nothing, there's no change, there is no difference. So you're going to write mu of diastolic blood pressure at stage 1 is equal to mu of diastolic blood pressure stage 2. This is our null hypothesis. The alternative hypothesis, however, is going to say that these two are not equal. The second step is where we assume that the null is true. Okay, we're assuming the null is true. And we're going to set alpha at 0.05. Now excuse me because I forgot to write this in the pair t-test setup. Since these are pair, it's the same woman measured twice, I can write that the mu of diastolic blood pressure differences between stage 1 and stage 2 is equal to 0. And the alternative hypothesis is that the mu differences in blood and diastolic is not equal to 0. Okay, they are equivalent. These two are exactly equivalent to one another. Step number 3, I need to calculate my what is called now the, you should call it the pair t-test, where the formula is d bar. We're going to divide it by standard deviation of the differences divided by square root of n, and n is the number of pairs. Let's calculate d bar s and n quickly. Okay, I already had set it up here. You have stage 1 and stage 2. These are the diastolic blood pressure, stage 1 and stage 2. I'm going to calculate the difference between the two. It doesn't matter which one you do, so this time I'm going to do stage 1 minus stage 2, just to show you that you can do either. Okay, so these are the values of the differences. I'm going to calculate the means and I'm going to calculate the standard deviations. All right, so I can use my formula that says average, and I identify the data and standard deviation. Remember, for standard deviation to always use the standard deviation of sample, and by a simple cut and paste. So here's my D bar, negative 3.25, and the S is 3.955. Go back to here, negative 3.25 divided by 3.955. 3.955, and this is divided by the square root of, if I'm not mistaken, 8, because the sample size was 8, so I had 8 every time, so the n. So this is equal to what? Let's do the calculation quickly. What I need to do first is calculate the standard error, which is the standard deviation divided by the square root of 8. All right, and then if you calculate t, d bar divided by this number, and negative 2.32. Go back here, so it's negative 2.32 for degrees of freedom 7. Okay, so remember this negative 2.32. We're going to see the t table now. All right, degrees of freedom 7 is right here. I'm looking for negative 2.32, right? Okay, so go back to the t table. So actually, if you remember, let me just remind you what is the t. If you remember, this is the t distribution right here. What the p-value is going to be as extreme as, meaning you're going to take this area right here, go down, and multiply by 2. Okay, so it's actually 2 times the probability of t less than negative 2.32. But from working on the t table, you remember that the t doesn't give you the positive, so you have to do something with that. And the way you're going to turn this into a positive is either you change the direction, or you do 1 minus. So basically, we're going to do 1 minus the probability of t less than the positive value of 2.32. And then all of that, we're going to multiply it by 2 right here. Okay? Okay, so let's go back to the t, degrees of freedom 7. I'm looking for 2.32. Mafi 2.32. There's 2.36. I'm not going to use it. I'm just going to say this is a bit too big. So I'm going to say that my t is somewhere here between the 1.8946 and the 2.36, meaning that the areas where my t is in between is 0.95 and 0.975. But remember, I need to do the 1 minus. So 1 minus 95 and 1 minus 975 is going to yield 5% and 2.5%. And now I need to multiply by 2. So the 5% becomes 10% and the 2.5% becomes 5%. And therefore, I go back to my p-value. My p-value, I'm going to write it here, is between the 0.1 and the 0.05. Okay, let me rewrite the whole thing. Okay, so we've calculated a t, and out of the t we're able to get a p-value, and based on what we've done so far, we figured out that the p-value of this specific question is between 0.1 and 0.05. Now remember, our alpha was 0.05, therefore our p-value is definitely greater than alpha. And what happens when our p-value is greater than alpha? We fail to reject the null hypothesis. Okay, and the null hypothesis used to say what? that the mu of differences is equal to 0. Or another term, there was no difference between the before and the after. Let me show you again what was the question. Okay, that was the null hypothesis. It was about that the stage 1 and stage 2, there's no difference. And we do not have evidence to support that there is a difference for the diagnostic arterial pressure for these women because we failed to reject. Okay, so the way we're going to formulate our research conclusion is to say that there's no evidence to support that the diastolic arterial pressure at these different two stages are different, and that's the end of our analysis. Before I finish, let's go back quickly. So if you remember, the average diastolic blood pressure was 69.75 at stage 1, 73 at stage 2. The difference was negative 3.25. And what we're saying is that the differences are not big enough to declare them to be what we call now, maybe that's a good time to start using these words, statistically different. Okay? So we failed to detect a difference between these two, and the differences that we observed between these two is just an artifact of sampling. So we say that the difference is due to chance only. It's a sampling issue. Okay? I hope you enjoyed this lecture. What I'm going to do in the next is I'm going to introduce what do we do when the two samples are not paired, they're not the same people. How do we analyze the data? And once I do that, I'm going to do a lecture using the PowerPoint that you have on Blackboard.